Assalamualaikum, nama saya Nurul Humaira Maisara, nombor matriks 07 DKA5C saya akan membentangkan slab bagi projek kami. First, for the specification, terminal load bagi GK ialah 9 kN per meter square. For the variable load GK 3 kN m square. For design life 15 years. For fire resistance R60 for exposure class X1. For the material, concrete strength FCK 35 N per mm square. For the steel strength FIK 500 N per mm square. For unit wet concrete 25 kN per m square. For the bar diameter, we assume as 10 bar mm. For the design slab panel, for our slab long span LY, we have 3,600 mm. For the short span LX, 3,500 mm. So, kita akan bahagikan LY per X dan kita akan dapat mendapat jawapan 102 mm. So, itu dikira sebagai two-way slab. Untuk analisis kami pula, since kami punya adalah two-way slab, so kami adalah case 4, which is two adjacent edge discontinuous. For the bending moment, bagi short span kami ialah mx1 adalah 4.65 kN per m square. Bagi mx2, 6.07 kN per m square. Bagi long span pula, my1 adalah 4.39 kN per m kuasa 2. Bagi my2 pula, 5.82 kN meter kuasa 2. Bagi reinforcement pula, bagi effective depth, dx kami ialah 95.0 mm, bagi dy 85.0 mm. For the minimum and maximum reinforcement area, AS min kami adalah 0.26 darab 3.2 bahagi 500 darab 1000 dan darab 95. So, yang kami dapat adalah 161 mm square per m. Bagi SAS max pula, 0.04 darab 1000 darab 125. So, jawapannya adalah 5000 mm kuasa 2 per m. Seterusnya, kita akan buat sambungan pengiraan bagi main reinforcement. So, bagi short span, kita akan ambil mid span sahaja, which is mx1 iaitu 4.65 kN per m square. So, pengiraan bagi akhir bagi mid span adalah AS sama dengan m per 0.87 darab FYK darab Z. So, 4.65 darab 10 kuasa 6 sebagai m, kemudian bahagi dengan 0.87, bahagi darab dengan 500 darab 0.95 darab 95. Jawapan yang kita dapati adalah 118.44 mm square per m. Bagi support pula, kita akan ambil yang kedua, which is mx2. So, 6.07 kN per m square. So, jawapan akhir, pengiraan AS adalah sama seperti mid span tadi. So, AS sama dengan 154.62 mm square per m. Seterusnya, kita akan pindah kepada long span pula. Bagi long span, sama juga seperti short span, which is mid span. Kita akan gunakan yang kedua bagi long span, which is my1 sama dengan 4.39 kN m square. So, jawapan AS dia, untuk makluman, AS juga sama seperti yang di atas, seperti short span. So, AS sama dengan 124.98 mm square per m. Bagi support pula, jawapan akhir bagi support adalah 165.69 mm square per m. Kemudian kita pindah kepada shear. So, design shear force bagi VED ialah 14.19 kN. Bagi shear resistance pula VRDC ialah 61.61 kN. So the result is VED lebih kurang daripada VRDC. So no shear links required. So which means slab safe in shear. Last but not least, for deflection check, allowable span L per D adalah 93.15. Bagi actual span L per D 36.8. So actual lebih kurang daripada allowable, so it's pass. For the crack control, main bar spacing adalah 400 mm, so dikira okay. Bagi secondary bar spacing lebih kurang daripada 450 mm, so okay. For the conclusion, strap safe in bending, safe in shear, safe in deflection, all bar spacing comply with Euro Code 2.
Saya Dayang Nur Yasmin Nadira binti Muhammad Yusri, nombor matriks 07 DKA5C1043 akan membentangkan beam 1 simply supported beam. Berdasarkan beam dari design projek yang kami pilih, span bersih iaitu LN bernilai 6000 mm. Untuk efektif span pula LF 6250 mm. Bagi permanen iaitu GK 1.35 kN per meter. Dan untuk variable iaitu QK 3.0 kN per meter. Untuk material pula, strength of concrete FCK 35 Newton per millimeter square. Untuk FYK iaitu strength of steel 500 Newton per millimeter square. Untuk material ini kami assume bar 1 20 mm, bar 2 16 mm dan bar link pula 6 mm. Untuk size pula overall depth H iaitu 481 mm dan width iaitu B 192 mm. Tetapi kami akan menggunakan P darab H 200 darab 500 mm untuk seimbangkan pengiraan. Bagi C-norm pula iaitu nominal cover, bagi desain ini kami menggunakan 35 mm. Bagi loading dan analysis pula, design action yang kami dapati iaitu WD 9.70 kN per meter. Seterusnya kita akan kira shear force dan masukkan nilai yang kita dapati tadi iaitu WD dengan L ke dalam rumus shear force, iaitu V sama dengan WD L per 2 dan kami dapat bernilai 30.31 kN. Untuk bending moment pula, M sama dengan WD L kuasa 2 per 8 dan kami dapati nilai 47.36 kN meter. Bagi effective depth, D kami mendapati 439 mm dan D prime 49 mm. Bagi design bending moment MED 47.36 kN meter dan kami mendapati K bernilai 0.035. Untuk kabel pula ialah 0.167, bererti K lebih kecil daripada K bulk. Jadi di sini bermaksud compression reinforcement is not required. Dan nilai Z pula bernilai 426 mm. Jika compression reinforcement is not required, kita akan menggunakan area of tension steel sahaja. Jadi AS sama dengan 256 mm square dan kita akan gunakan 1H20 bersamaan 314 mm square. Bagi minimum and maximum reinforcement area iaitu AS min, kami dapati 114 mm square. Bagi AS max pula 4000 mm square. Bagi shear reinforcement, design shear force VED yang kita dapati tadi ialah 30.31 kN. Dan kemudian kita akan proceed kepada next step iaitu kira VRD max dan nilai yang kita dapati adalah 330 kN bagi 22 degree dan 476 kN bagi 45 degree. Untuk kedua-dua VRD max yang kita kira tadi bernilai lebih besar daripada VED. Dan kita teruskan kepada pengiraan bagi shear links dengan minimum links. Untuk shear resistance of minimum links iaitu Vmin, kami mendapati bernilai 813 kN. Jika dimasukkan kepada links arrangement dan kami akan kira X, kami dapati negatif 80.7 meter. Bermaksud Vmin kami lebih besar daripada VED iaitu shift force yang asal. Jadi di sini bermaksud links arrangement terdapat error kerana Vmin lebih besar daripada shift force yang asal membuatkan tidak seimbang bagi pengiraan ini. Berdasarkan pengiraan, daya tegangan FTD ialah 37.6 kN dan keperluan tertulang longitudinal adalah 86.4 mm per square. Jadi, 1H per diameter 20 dipilih. Untuk deflection, menunjukkan nilai L per D actual ialah 127.6, manakala nilai allowable hanya 65.6, menjadikan deflection tidak memenuhi syarat. Namun begitu, untuk kawalan retak, jarak par maksimum yang dibenarkan ialah 200 mm dan jarak par yang digunakan ialah 49 mm. Jadi, ia memenuhi keperluan cracking. Secara keseluruhan, reka bentuk ini mematuhi keperluan cracking tetapi gagal pada deflection.
My name is Elton Garcelaban Singh, card matrix 07 DKA5C, and now I am going to explain for the beam 3 calculation. So for beam number 3, this document details the initial structural design specifications for continuous reinforced concrete D-beam outlining a 4,300 mm span, 225 mm times 500 mm beam width, 110 mm slab thickness, 35 Newton per millimeter square concrete strength, 500 Newton per millimeter square steel strength, and this calculates the critical which 1345 mm to 1845 mm effective flange width be effective, and establish the ultimate permanent load GK, which is at 5.35 kilonewton per meter square, and the variable load QK is 3.00 kilonewton per meter square. So for this part, the load calculation enforces the total slab load is converted into a heavy line load that the beam has to carry, which the total permanent load are 6.38 kilonewton per meter. The total variable load is 9.00 kilonewton per meter. So these are factored up to get the extreme ultimate design load, which is used to safety checks. This load creates a maximum bending moment in the middle of the span AB to CD equal to 154 kilonewton meter. So now we need to find the steel needed. The calculation uses this maximum force to find the required area of steel bars to prevent the beam from failing. So the effective depth, this is the depth used for calculation, which is 454 mm. So the required area of steel reinforcement for this section is 800 mm square. So this required steel area is checked against the minimum 132 mm square and maximum 4500 mm square limits to ensure the design is valid. The 800 mm square falls within these safe limits. So for this part of the calculation determines the required steel reinforcement for two critical sections of the continuous beam, the mid-span span BC and the support BC. So span BC, this calculates the steel needed at the bottom of the beam where it bends downward. So the bending moment, the force is calculated as 80 kilonewton meter. Neutral axis check, the calculation confirms that the beam's stress limit is 0.012, which means the compression zone is well within the 110 mm slab flange. So the steel result, the required tension steel area for the bottom of the beam is 426 mm square. So for the support BC, this calculation, the steel needed at the top of the beam where it bends upward. So for the bending moment, the force over the support is much higher at 157 kilonewton meter. The stress ratio is 0.107. The compression still checked because the bending moment is so large, so that the calculation shows that the compression still will have yielded. Means the concrete alone can't handle the compressions and extra seal is needed in the compression zone. So the primary steel area needed at the top of the beam is 758 mm square. The required compression steel area for the top of the beam is 704 mm square. In short, span BC needs 426 mm square of steel at the bottom, but the support section needs much more steel because the bending forces are significantly higher there. For this part, this shows the details that the shear reinforcement design for the T-beam, calculating the vertical links needed to resist diagonal forces near the supports. As we can see, the design ensures the links are sufficient by checking against the concrete's maximum shear capacity, 384 kN to 558 kN. Additionally, an additional 195 mm square of longitudinal steel is required at the end supports and 259 mm square at the internal supports to anchor these shear forces. So for this part, in summary, the beam needs minimum links where the shear is low, extra main steel to resist shear effects, and hedge 10 to 260 mm links running across the slab to prevent the slab from shearing off the top of the beam. So as you can see here, for the cracking control, the actual calculated bar spacing 66.5 mm is less than the maximum allowable spacing 100 mm. So the design is okay for cracking. So for deflection check, this ensures the beams isn't too shallow by comparing the actual span to depth ratio to the maximum allowable ratio. So since the actual ratio 9.47 is much less than the allowable ratio, which is 46.4, the beam is stiff enough and the design is okay for deflection.
In this slide, I begin by introducing the key dimension of the column and the beams connected to it. The column section is 275 by 350 millimeters, and the story height vary from 1.5 meters at the footing to 4 and 5 meters at the upper level. I also list the beam size and their span because these beams transmit loading into the column. Finally, I summarize the permanent, variable, and the design action. These design loads are essential because they will be used later to calculate the axial force and bending moment. Okay, next, I calculate the axial force acting on the column, starting from the upper floors and moving downward. The axial load at any level is the sum of beam reaction framing into the column plus the self-weight of the column segment above. For the first floor, the loads contributed by beams 2 per AC and B per 1/3 are added, and the column self-weight is included. This results in an axial force of about 55 kilonewtons. Proceeding downwards to the ground floor, additional loads accumulate, giving us approximately 113 kilonewtons. A similar process is repeated for the lower column until we reach around 100 kilonewtons at the base. Next, we move on to bending moment calculation to distribute moment correctly. We first determine the stiffness of each column and beam segment using I per L. The stiffness values vary based on length and section size. Then, using the fixed end formulas for uniformly distributed loads, we compute the moments at each end of the beam. The difference between these fixed end moments give us the unbalanced moment, which must be distributed into the connected members. This slide applies the moment distribution method. Using the unbalanced moment computed earlier, we distribute it to the upper and lower columns according to their stiffness. Since the stiffness ratios differ, each member attracts a different portion of the moment. Here, the upper columns take about 0.07 kN meters, while the lower column attracts a larger moment due to greater stiffness. The moment diagram on the right illustrates the final distributed values. We repeat the moment distribution procedure for the second loading case. Again, the fixed end moment are calculated, giving an unbalanced moment of about 3.78 kN meters. Using the stiffness ratios, we distribute this moment between the upper and lower column. The upper column receives around 0.48 kN meters, while the lower column carries about 1.60. These values will later be combined with previous case if needed. This final slide summarizes the moment distribution results graphically. The upper and lower columns attract 0.48 and 1.60 kN meters respectively. The diagram on the right captures the complete moment distribution and give us a clear view of how the bending moment varies through the column. With this, we complete both axial and moment analysis for column 2. That's all from us, and thank you.